In this video, I'm going to discuss the pseudocode and time complexity analysis of quicksort algorithm. So first let's discuss the pseudocode, and later on we'll discuss the time complexity as well as the scenario of each and every cases, best case, worst case and average case. So first let's discuss the pseudocode. So algorithm quicksort, there is low means the very first index and high means the last index. So the very first condition is if low is lesser than high. Why this condition means, like, only when there is more than one element in an array the sorting algorithm works. When low is equals to high, which means there is only one element in an array, the sorting algorithm need not to be applied over there. So when there are more than one element, the sorting is required. So to check whether there are more than one element, this is the condition if low is lesser than high, which means there are more elements, more than one element in the array. So we can perform the sorting operation. So the first step is, like, normally what we used to do means we used to partition it, right? So there is low and high pointer are there, we are supposed to partition the array. So when exactly the array would get partitioned means when we perform the swapping operation with the j and pivot element, as we discussed in the last video and in the example, like, the partition would happen when you swap the pivot element, right? So the partition would happen. So when partition would happen, so for performing the partitioning operation, the code has been written here, we'll discuss it later. So once the swapping is done, the partition would happen. So the two subarrays would be getting, one is the left subarray and another one is the right subarray. So we are using the recursive call here recursive function quicksort. So this quicksort would be called for what, to handle the left subarrays. So the left subarray range is going to be right from low till j is, just imagine j is the pivot element. If j is the pivot element, till j minus 1 it is going to be the left subarray, and the right subarray should start from j plus 1 till high. That's what they have given. Low till j minus 1 is going to be the left subarray, j plus 1 till high is going to be the right subarray, which is going to keep on checking it. If low is lesser than high, you are going to keep on performing the partition. Once partitioning is done, we would be getting two subarrays, left subarray as well as the right subarray. So now let's check how to perform the partition. Partition means how are we going to do some processes and make the perform the swapping operation. We are going to change the position of the pivot to its right position. Let's discuss now. So algorithm partition, it has been given here. The very first step is to perform the partition. You are supposed to choose the pivot element. Either you fix the first element as the pivot element or last element as the pivot element. So here in my example, I have considered the first element as the pivot element. First element is array of low. So I have chosen array of low as the pivot element. Now, and the next step is define I and j variable. So I variable would be pointing low minus 1 and j variable would be pointing the low plus 1. I would be pointing low plus 1 index and j would be pointing the high index, which means the last index it would be pointing. Now you have to, there is a loop. The condition here is while I is lesser than j. So as far as the I is lesser than j, like, we can increment I pointer, but the condition is for incrementing the I pointer while array of I is lesser than or equals to pivot. So if array of I is lesser than or equals to pivot, you can keep on incrementing the I pointer, and also you can keep on decrementing the j pointer. So to decrement the j pointer, the condition is while array of j is greater than pivot. So you can keep on incrementing the pointer I pointer and keep on decrementing the j pointer. At certain point it would stop, right? So you have to check that time where if I is lesser than j. If I is lesser than j, you are supposed to perform swapping between array of I and array of j. If I is greater than j, you are supposed to perform the swapping between the pivot element as well as the array of j. So once the swapping is done, the partition is over. So again you will start getting the left subarray as well as the right subarray. Apply the same process again here and come to the partitioning section, perform the partition. Again you get the left subarray and right subarray recursively until the entire elements in the list is sorted, in an array is sorted. So this is how the quicksort pseudocode works. Now let's move on to the time complexity analysis. So here, if you check the worst case time complexity of quicksort algorithm, it's going to be big O of n square. I'll discuss it, like how the n square came, it will be discussed later. But if you check the worst case time complexity of quicksort, it's n square, but if you check the merge sort, it's going to be only n log n, but here the worst case complexity is n square. When it comes to best case, the complexity is going to be n log n. Later on we'll discuss the scenario under each and every cases, and omega of n log n and for average case it's going to be theta of n log n. Let's discuss the scenario of each and every cases. First I'll discuss the best case scenario of Quicksort algorithm, and then I'll tell you the worst case analysis. So, okay, the best case time complexity is omega of n log n. So, the best case scenario for Quicksort occurs when the pivot is chosen such that it evenly divides the array into two subarrays of roughly equal size. So, in this scenario the Quicksort exhibits its optimal performance. So, we would get only big O of n log n in the best case as the best case. So, each partitioning step divides the array into two equal parts, that would resulting in like you would be getting finally the big O of omega of n log n complexity on the best case. So, the example is in the previous video we discussed two examples, right. So, if you look at the example 1, so here yes, the list is getting equally divided into two subarrays, right. And if you check, yeah, this is the list, this was our example. Let me change the color. Okay. So, this is the example, right. If you look at this example, if you perform the partitioning operation in the next step, once the pivot is swapped, if you check, the pivot has exactly came to its the right position, which is in the middle of an array. So, all the remaining elements, if you check, we got two equal subarrays we have got, right. So, this is what we call it as a best case scenario. So, the best case scenario is like the pivot is, when the pivot is chosen, it should evenly divides the array into two equal subarray. So, this is what the best case scenario is. So, the best case scenario, this is this example best suits for the best case scenario. When it comes to the worst case here, the worst case complexity is n square, I said, right. So, when exactly we would get n square means like when you choose, like either you can choose the first element or last element as the pivot element, I said, right, in the example. So, here like while choosing the first element or last element as the pivot element, either first or last as the pivot element, if that pivot element is going to be the largest element out of all other elements, or else the smallest element out of all other elements, means it would end up with n square complexity. Let me tell you how. Like we will take one example. Okay, this is the example, example number 1 for the worst case scenario. So, which is going to like show the worst case scenario here. I'll take this example 80, 65, 40, 75 and 45. So, as per the algorithm, we are going to fix our first element as the pivot element. So, this is going to be our I and this is going to be our j. So, here if you check, like all as usual, I is lesser than pivot element, you can increment I. Again I is lesser than, yes, I is lesser than the pivot element array of I, so you can increment I. Again array of I is lesser than the pivot element, so you can increment I. So, I is here, again I is lesser than the pivot element, so I can be incremented. Again if you check array of I, there is no array of I cannot be incremented anymore. If you check j is lesser than the pivot element, so j also cannot be decremented. So, in this scenario you have to check whether I is lesser than j, no, I is greater than j. If I is greater than j, you have to swap j and pivot, right. So, if you perform swapping between j and pivot, 45 is here and 80 would go to the last position. So, once if you change the position of the pivot, you are performing the swapping between the pivot and j, the pivot would always go to the right position, right. So, the pivot is in the right position now. If you check whether the list got divided into two equal halves, no, right. So, what happened now? There are n number of elements, the problem size were n initially. Now, after performing the swapping operation, the problem size became n by n minus 1 instead of becoming n by 2. There must be n by 2, right. So, but here it is n by 2. So, in this scenario, the complexity is going to be n square. So, the recurrence relation is going to be completely different, because every time like whenever like you are solving the problem for each sub problem, either if you pick the largest or smallest element as the pivot element, it would end up with n square only. Let's take one more example, example number 2 for the worst case. Okay, the list is already sorted, so here it's an unsorted order only. The list is unsorted only, but still if you choose either largest or smallest element as the pivot element, you would end up with n square complexity only. The complexity is going to be n square. The next scenario is, the list is, if you want to sort the list in the ascending order, but the given list is in the descending order. For example, 7 6 5 4 3 2 1. This is the list, it's in the given in the descending order. I just want to sort it in the ascending order. So you can fix either first element or last element as the pivot element. If you fix the first element, it's going to be the largest element out of all other elements. Okay, if you choose the last element, it's going to be the smallest element out of all other elements, right? So both the cases are going to be the worst case scenario only. Still, I'm going to pick the first element as the pivot element. Now this is my I and this is going to be j. Compare array of I and the pivot. Yes, it's lesser, increment again it's lesser, increment it, again lesser, you keep on incrementing it, again it is lesser, you will increment it, there is no more I. If you check j, if you come to j is not greater, so j cannot be decremented. So here again I is greater than j, perform swapping between the pivot and array of j. So now 1 would come here, 6 5 4 3 2 and 7 would go there. So 7 is the pivot element, it has come to its right position. Now the problem size is not n by 2 n by 2, there is no right subarray at all, only one subproblem is there, that subproblem size is n minus 1. We'll move on to the next iteration, there is only left subarray, right? So again we'll make an attempt to solve the left subarray. So this is our pivot, this is I and this is j. You just compare array of I should be lesser than the pivot element, right? But array of I is not lesser than the pivot element, it's greater, so I cannot be incremented. Then again I cannot be incremented, just move on to j. J is lesser only, decrement, again j is lesser, decrement, again j is j should be greater, yes j was greater, so 2 was greater, decrement, again 3 was greater, decrement, again 4 was greater, decrement j, again 5 is greater only, decrement j here, again 6 is greater, decrement j, it would swap by itself, right? So 1 would remain in the same position only. Again if you check, the problem size was initially n, again like after performing the swapping operation, the subproblem size became n minus 1. So every time, like whenever you make an attempt to solve the subproblem in each iteration, you are getting only the subproblem with the size of n minus 1. So in this scenario, you would be getting the complexity only big O of n square only. Why? Because for the worst case scenario, the recurrence relation is going to be, is going to be T of n equals to, let me explain. For the worst case, it's going to be T n minus 1. You all know T of n means what? Time taken by the Mozart algorithm for the input size n. So for the worst case scenario, the recurrence relation is going to be T of n minus 1 plus theta of n. So the problem size every time is going to be not n by 2, n minus 1, and also the number of subproblem is only 1, right? So if you solve this recurrence relation, if you derive this recurrence relation using any of the method like substitution method or Master's theorem, you would be getting n square as the complexity. So the worst case scenario of the quicksort algorithm is big O of n square. Now let's move on to the best case scenario. So the best case complexity is big O of n log n, I said, right? So the recurrence relation for this is going to be, already I explained you the scenario, the best case scenario. So for the best case scenario, the recurrence relation is going to be T of n equals to, best case means where like if the pivot locates exactly in the middle of an array. So if it comes to the middle of an array, definitely like both the subarrays would be in equal size only, right? So the recurrence relation is going to be 2T n by 2 plus n. So 2 is the size of the subproblem, this 2 is going to be the size of the number of the subproblem. So like every time we would get 2 subproblems and both the subproblems would be solving. So the coefficient is going to be 2 and this n by 2 is going to be the size of the subproblem. Size of the subproblem, this is number of subproblem every time when you partition it, and this n is going to be, this n represents time taken for the partitioning step. In the best case, the partitioning step efficiently divides the array into 2 nearly equal subarrays. So if you solve this recurrence relation is same as the merge sort algorithm only. So if you solve this recurrence relation using Master's theorem, you would be getting the answer n log n. So the best case time complexity of the quicksort algorithm is omega of n log n. So here also this n indicates the time taken for the partitioning step only. So now the best case scenario and worst case scenario is explained along with its recurrence relation as well as the time complexity. And if you look at the average case, again the average case is also the same, which is big O of n log n only. Assumes it's a random distribution of elements. Again, if there is a random distribution of elements in the input array, we call it as the average case. So in this scenario, like this quicksort demonstrates excellent performance when it comes to the average case scenario. So if you check in the merge sort, the thing is, like, especially when during the worst case, the complexity is going to be big O of n square, right? So, and the average case is still n log n. If you want to make it as n log n only, you can go with, you can prefer the randomized quicksort algorithm. If you prefer the randomization algorithm over it, you will be able to end up with n log n number of iterations only for the quicksort. Thank you.